the keyboard here, I guess. All right. Oh, there we go. Now it's working. So a little bit about me, about my education, like Professor Quan Nguyen just mentioned about. I completed my master's, sorry, my bachelor's of science in mechanical engineering in Loyola Marymount University in 2020, and then subsequently I joined USC and started doing research with Professor Nguyen, and then until today we had many fruitful results in the realm of hierarchical optimization with the focus on dynamic locomotion and manipulation on humanoid robots. Right, so this is current list of contributions we have, as well as some collaborative works we have done throughout the years. Um, and just a quick overview of today's presentation before we, get into the details. Right, so I'll introduce some background, motivation, and challenges in the realm of humanoid, and as well as some, basics of local manipulations. Right, and then our research will focus. The first part of the research will focus on establishing a baseline control method with model predicted control for humanoids, mostly in terms of locomotion, so we can establish and extend this work to other realms, right? And that from there, our research developed into two directions. One is for dynamic locomotion via adaptive frequency control. That's realizing real time and adaptive behaviors on humanoids in terms of locomotion. And then we'll focus more on the whole body local manipulation control for the second parallel branch here. And then to sum up, we'll bring some of the inspirations and lessons we learned from these previous research, and then merge the adaptive frequency control with local manipulation at the same time, adding some learning augmented components to the MPC here. Okay. So let's get into this. The main problems we try to investigate here is how to represent the locomotion and manipulation control behaviors through proper design of hierarchies, models, and solving mechanisms even within the hierarchical optimization to achieve very robust, adaptive, and efficient behaviors. All right, so that's through the means of adaptive frequency control, reduced order modeling strategies in the optimization, and also learning augmented components for the optimization-based control. All right, so all of that will be validated through extensive experimental results and validations. Okay, so now I will go over some motivations and challenges of studying humanoids or local manipulation in general. All right, so more recently we see these increasing labor shortage within US or even within the world, and then specifically after the pandemic, we see more of these work-related infidelity and also these inflations as well as increasing worker count. So driving these industries try to consider more automated options for replacing labors, right? So humanoid being one of them. And I like to call it the age of humanoids right now, not only because of the hype, but also I think it is the technology and embodied intelligence is converging to a point where humanoid form factor could be a well-suited option for many of these streamlined works within the industries within different scenarios. Okay. And why humanoid, you may ask, right? So just like humans, a humanoid has the potential to be as agile as humans and also has the high degree of freedom on their body to do different kind of tasks, right? Like traversing different terrains, uneven terrains, and even gaps, and where the wheeled robots are mostly not able to traverse, right? And then on top of that, it also is able to use the arms to do more of these manipulation works and mimicking how humans do their whole body manipulation and doing their, dexter hand manipulation and all of that. So it becomes more difficult to combine locomotion and manipulation together because this area is still sort of underexplored, and then people are still trying to figure out what is the best way to represent these nice coordinated behaviors in terms of motion control, right? So speaking of the challenges, right? So because the humanoid robot is inherently unstable, just like humans, right? Has high COM location as well as very small support region during walking. It is already very challenging and underactuated in these walking behaviors already. So we see even under if we put payloads onto it and do some manipulation while doing locomotion, it becomes even more difficult. Okay, and current forms of these humanoids in the industry, we see more of these quasi-static behaviors, walking with slow speed or doing local manipulation with simple these simple tasks, right? So with that, you see it's really hindering the full dynamic capability of these high degree freedom robots, right? So what we want to do is we want to focus on more achieving these dynamic, efficient whole body local manipulation. So our journey will start with locomotion and then and then convert to the point where you can do dynamic local manipulation. Okay. All right, so I'll introduce a little bit background in this topic, especially local manipulation and motion control and on humanoids in general, and then I'll try to cover a bit of a background on the modeling strategies as well as the hierarchical optimization in general. Okay. So speaking of the evolution of humanoid robots, right? We see a lot of these, different platforms coming out these years. So back in 2000, year of 2000, we see some steady progress of humanoid hardware, both in academia and in the industry. And then around 2010, 2015, we see more of these platforms who are doing a lot of, more hands-on and also realistic scenarios due to the DARPA Robotics Challenge, right? And then afterwards, we see more of these dynamic and more capable hardwares coming out. And until like around 2023, 2024, boom, there's like 40, 50 new humanoid robots companies doing humanoids and their own in-house humanoids, right? Not only because the hardware is more accessible at that point, but also on the other spectrum, motion control becomes sort of easier for these individual companies to establish their own control stacks. Right. Um, I'll present that later. I have some nice videos of it. Yes. Yeah, so for the motion control, we also see a very nice steady progression of different techniques, right? In the earlier days, we see more of these heuristic-based, simplified model-based control method. For example, this is a Honda Simo working with ZMP-based control that is pretty nice back in the day, around like 2003, 2003 and somewhere there. And we already see these nice position-based control behaviors. And then later on, we see more of these formal analytical solutions, analytical derivations of dynamics or different methods that can represent the humanoid dynamics a little bit better. And this is the Atreus robot doing HCD-based control with, I believe, only a few hundred lines of code that can achieve this nice of a behavior here. Okay. And then more recently, we see these whole body control, NPCs, hierarchical optimizations, and even learning-based control. And that's thanks to the bloom in computation hardware and the resources available nowadays that can do much more of a coordinated control, right? And if we categorize these methods, right? So the earlier days, we see more of these position-based control that's mostly due to the harmonic drive and then the limitation on the hardware itself, right? And also the computation. And later on, we see more of this force and torque-based control that is more compliant, more adaptive to different disturbances, and we'll be able to, have this sort of nice backward drivability on the hardware as well. And if we categorize even further, the earlier days, we see more of these closed-form analytical solutions that is, with the limits of the computation online. And nowadays, we see more of this optimization-based and even learning-based that's using extensive resource to do both offline and online control for a better, motion behavior. Okay, and also due to that, we see the locomotion focused are mostly the earlier days, and then we see now we're doing more of these locomotion and manipulation, or is more capable of doing these two together. All right. So for example, we see here this is a nice video from Boston Dynamics back in 2019. The Atlas doing the obstacle course navigation and locomotion, right? So that's through hierarchical optimization. And then later in the day, nowadays they're doing these imitation learning-based control. So kind of you see that evolution from model-based to learning-based method, right? For locomotion itself, right? But if we talk about local manipulation in general, this trend is a little bit different because nowadays we still see This is a video that came out just a couple of days earlier, and then we see some of these nice local manipulation behaviors still based on MPC and hierarchical frameworks, right? So they have their vision stacks on top, and also have some behavior models, and also they use their state-of-the-art MPC method to do most of the motion tracking and control, right? So what we try to focus on is also we're trying to do this hierarchical MPC or optimization-based control to achieve nice manipulation behaviors and local manipulation behaviors in general. Okay? Right. So speaking of that, of hierarchical optimization, modeling strategy is a very important aspect, and I want to give a quick background on some of the models you will hear throughout this talk, and specifically, regarding, the fidelity of these models. So on the highest fidelity, we have what we call the whole body dynamics. That is pretty much using a full order model, and then, even you see this is a very standard or simple equation there. Lucas there always tell me it's gonna, if you write this everything out symbolically, it will cover the entire football field with this letter-sized paper, right? So it's definitely too hard to do, this online control, or too computationally intense to do online control with, even predictions ahead of it, right? So that's why we look into these different kind of reduced order models. So centroidal dynamics being one of them is able to do some of these nice behaviors with assumption that all the link inertia is projected to the COM space and actuated by these virtual contact points. Okay, and then if you want to categorize a little bit further, you see this kinodynamic model that is using a kinematics relationship within the dynamics formulation of the centroidal dynamics, and able to do more of these joint level constraints, and that is more realistic, what we call like a whole body behavior. And then at the end of the spectrum, the centroidal dynamics, if we fix the inertia of the body, we call it a single rigid body model. That is pretty much one of the simpler form of the modeling strategy here, which is also what we are gonna focus on a lot in this talk. If you look at the spectrum here, the model fidelity increases from right to left, and also with the compromise of computation speed. So our goal is try to use hierarchical optimization to choose between different kind of models, or mix and match different models for a kind of like somewhere in between. To be able to do high fidelity control, high frequency control at the same time, where we're doing some of the model simplification, so it does not need that much of a computation resource online. Okay. All right, so speaking of that hierarchical optimization, this is a general framework that we use for a lot of our control method. And so we can categorize into high, mid, and low level, where the high level is mostly a multi-contact planning strategy that is using, some sorts of trajectory optimization to plan for a long-term trajectory or these contact sequence and contact locations. Whereas the mid level is more of using MPC to generate a short-term look ahead, and also a control action generation. And those control action will be thrown into a low level for a task space or joint space executions, right? So our talk or our research will focus more on the mid two levels, the high to mid level, right? Using different modeling strategies and different combination of optimizations to achieve very dynamic behaviors. All right. So with that, we can get into the first part, which is a baseline force and moment-based MPC method. That is, we're trying to represent a humanoid dynamics model with simple yet efficient and effective inside of the hierarchical optimization, and setting up this MPC method as our baseline so we can derive and develop upon this one. All right, so also go back to that hierarchical optimization with single rigid body. Now you see this mid-level here, we replace it with the MPC method. And then the goal or the objective is to choose a representative dynamics model for this mid-level, so it's efficient enough, and also at the same time is adaptive to different kind of like these disturbances, and being very robust. So the first thing we tried is the single rigid body model across the spectrum of models, right? And if you look at our kinematics of a robot, we also have a line, what we call a line foot. So it does not have any like roll joint at the ankle and does not exhibit any like surface contact with the ground. Right, so with that, we need to carefully choose these contact wrenches, right? So now we have 5-degree freedom contact force and moments at the foot for the single rigid body model, and then we can formulate a dynamics that is representative to this dynamic model, a very simple dynamics model here, right? And then with that dynamics model and with some high-level heuristic-based contact planner to take care of this R variable here that is predefined, so we can get rid of this bilinear product here. And with also a small assumption, a small angular velocity assumption, we can fully linearize this dynamics equation. So now you see we can put it into a state space form with the proper choice of state variables and control input we just mentioned, and put it into an MPC with discretized dynamics form with this model right here. All right. So let's get back to this hierarchy here. So with a predefined context schedule, these binary 0-1 context schedules, and we put it into a heuristic-based contact planner and use just this footstep planning, which you will also see later in this talk, and to generate these look-ahead of contact schedules for MPCs, right? So the MPC will be formed as a QP problem to solve very efficiently online to generate control actions, which are just contact forces and moment. And then we'll use the low level to map those forces to joint space commands. Okay, so we can even condense further that dynamics constraint within the MPC problem and put it into the class term. So with that, we can even reduce the computation of this MPC further, and then we can run this as fast as 300 to 500 hertz online, and then that will give us very adaptive and very faster reaction behaviors. Right. So with this simple MPC here, we can already achieve very nice balancing, walking. And that's all with this MPC here. Then I look into this problem here. If you push the robot, the robot will just kind of fail here, right? Let's look at this again and look closely to the setting right here. It's always fixed. It does not really adapt to any of these disturbances here, right? So we didn't want that, and we want something that is more versatile and that is more perturbation resistant behavior, right? So we look into how to address this fixed frequency schedule and how to adapt this frequency online. So that naturally leads to the next part of the talk, which is the dynamic locomotion via adaptive frequency control. And in this case, we want to use dynamic locomotion via the adaptive frequency behaviors within the hierarchical optimization through the means of variable frequency and the resolutions within the top level and the mid level optimizations, and to achieve very real-time adaptive frequency behaviors in locomotion itself. Okay. So the first investigation we started back in the day was trying to address some of these adaptive gate frequency locomotion on bipedal robot itself. So this is one of the very classic work back then. It's called the tower. If you look at the motion that it generates there, you see some of these velocity dips and spikes, and you see these decelerations, accelerations, going on in this motion. We wanted something that is more dynamics and more consistent in this walking, or for example, traversing these stepping stones, we wanted something that is constantly with constant high velocity, and also be able to adapt the gate frequency and stride length to cover these different gaps in the ground, right? So now we look back at the heuristic gate planner, or the footstep planning heuristic here. We see we always exhibit a proportional relation behavior of these next step location and step duration for each continuous step, and then if we fixed the velocity of the trunk, right? So with that simple intuition there, we can formulate a framework that adapts the gate frequency of the robot to traverse different kind of gaps on the ground. So that's the high-level idea. And if we put it into a optimization problem, we can, with the terrain knowledge of a obstacle course of a stepping stone terrain, and then assume a somewhat constant velocity that we command, and then we can back out a optimal step duration for each step to cover each stepping stone, and that step duration is then translated into MPC dt. That's due to our choice of fixed contact schedule and this bilinear contact schedule look ahead for the MPC. So we can use this kind of framework here to already achieve nice stepping stone behaviors on these robots, right? So we see adapting these gate frequencies and stride length while keeping a somewhat constant linear speed here, right? And when this work is ready, we our hardware was ready back then as well. So we wanted to see if there's anything we can do on the hardware, right? So if we can realize these nice adaptive frequency behaviors in real life. Okay, so the first thing we look at is the jumping behavior. Of course, is very cool and very intriguing. And inside the optimization or the hierarchical optimization, since we want to do somewhat more autonomous and continuous jumps, it will require us to do more of these online planning and real-time planning for these jumps, right? So we have to slightly modify the high level where we'll incorporate a real-time hierarchical trajectory optimization. That is, somewhat lightweight enough to be able to execute the optimization on the flight, right? So what we choose to do is a sort of a matching between different models for the optimization modeling, right? So we have different hierarchies of model fidelities for different phases, right? Takeoff, flight, and landing will all have different modelings based on the requirements of that phase. And also we'll have a adaptive or hierarchical trajectory resolutions. For example, for the landing phase, it will match exactly the frequency of the MPC so that we're not really wasting any resources for the look at or for the optimal trajectory itself. So that allows us to form a very efficient trajectory optimization problem, right? So within the optimization, we see we'll have these phase-specific constraints for each of these phases here. And since this is more of a multi-shooting problem, we will be able to solve more efficiently and more likely to converge to optima, right? And then we compare to our methods to this classic full dynamic space and kinodynamic based trajectory optimization, right? So for of course these dynamics models are more complex and then somewhat more representative of the whole dynamics of the model, whole dynamics of the robot, right? So the solve time will also increase quite a lot compared to our method. Even though we exhibit a bit more steps on the go, we see some of nice reductions in the solve time. So that will, under 1 second, that will definitely be able to do more of these online motion planning and jump control, right? So that is, when we deploy this on the hardware with this adaptive frequency hierarchical framework for the motion planning and control of the jump. So the robot sees that as a disturbance and just be able to cover it. And also jumping off a 20 centimeter block, right? Also land properly. And also jumping over, these boxes. Okay, so now if we go back to this problem here, with this success, can we really address the push recovery or nice locomotion behaviors to generalize into this disturbance rejection emotions, right? When we started, we looked at this work from OSU who are using reinforcement learning to achieve this nice push recovery behavior. Right? So if you look at the first step, always really fast and reactive. We want to somehow relate our method to this intrinsic learned behaviors, right, to mimic how it behaves with this nice adaptive behavior. So through the means of hierarchical optimization. So we propose a push recovery motion prediction scheme. On the top level, we use a nonlinear MPC method with a full dynamics model in the near horizon to capture all of these pushing or perturbation, and then using these reduced order models in the distant horizons to only evaluate the evolution of the COM states, or pretty much we classify them into unstable and stable states durations. So with that, with those durations detected, we'll be able to put it into a posture regulating gate frequency planner that pretty much just use heuristic policy to figure out a next step timing, as well as the duration for the next step to stay balanced. Okay, so with that, this heuristic policy will consist a stability regulation as well as a orientation regulation. So in this case, we use this step duration dt within our centroidal augmented single rigid body MPC, and use that to execute this adaptive frequency behavior online. Okay, so with this method, when the robot is under certain disturbances that is unknown, we'll be able to adapt the gate frequency and balance properly. And similarly, if we just do the pushing or the kicking of the robot, it will also be able to adapt its gate frequency or step duration to remain balanced. Okay, so comparing to some of these methods, we see, for example, the baseline single layer MPC as well as MPC plus whole body control of these hierarchical frameworks. Comparing to our method, we see a very nice performance gain over these when we compare the pushing force and the pushing moment of their maximums when exhibiting on the robot for it to stay balanced, right? So we see even with the whole body control that is using a full order dynamics model, our method with reduced order or these hierarchical models will be able to outperform this full dynamics and have significant performance gain over it. All right. So with that, that's the second part. And then parallelly, we're also investigating a whole body dynamics or whole body local manipulation control that is using trying to use reduced order dynamics as well as leveraging the context schedules and whole body motions to achieve very dynamic behaviors and efficient behaviors on humanoid robots. Okay. So the motivations, again, we mentioned previously, the current humanoid local manipulation is still kind of a simple pick and place that we see in many demos, right? So with these lightweight boxes and walking on these even terrains and only using these arms to hold the object and not fully manipulating, the manipulated object, right? And relying on whole body control to only figure out the dynamics and control actions for the current step, and not really using a lot of predictive features of optimizations within the control framework, right? So we want to extend to be more dynamics and to consider more of this control or the transition between context and also leveraging whole body motions of the whole degree freedoms of the robot to do local manipulation. Okay. Yeah. So that leads to sort of two major directions or two major tasks that we're looking at for local manipulation. So one is the object handling, right? So it's thinking about like holding a very heavy object, right? Or another case would be pushing or dragging a very heavy and oversized object, right? So these two options here. So the first one we're looking at, we need to figure out some sort of modeling, or specifically a simplified modeling. So developing upon our single rigid body model, right? We see here, if we just put a weight on the robot itself, it won't be able to sustain it after the sudden transition because it does not really consider the dynamics of the robot, the object here, right? So it is important to kind of consider both the dynamics and the robots and combine them together and then represent them in an efficient way, right? So that's what we came up with, two methods that we want to compare. So one is what we call the combined rigid body model, simply treating that object as part of the new rigid body and kind of merge it with the trunk of the robot, right? So that because of the left-hand side, the physical properties always change due to these context transitions or any of these movements, right? So it becomes very unstable when deploying this. And that's where we lead to our proposed approach is the external force model, where we simplify these dynamics of the objects into external force applied to the COM of the rigid body model. So in that case, we'll be able to, in that dynamics equation on the right-hand side, we'll be able to represent both the external weight of the object as well as the contact timings of the object. So the result is nice. After the sudden transition, we'll be able to hold a very heavy object successfully. Okay. So that's for the load handling part. And if we look into this dynamic modeling for the non-prehensile pushing task, right? So for example, now you have more of not only just the contact of object and the robot, right? So the interaction between the object and robot, but also you have the interaction between the object as well as the terrain or the ground or the environment, right? So it becomes more complicated, but we still want to reduce the computation load online and still use a somewhat reduced order model in this case. So we look into the pushing behaviors of a human, right? With very heavy and oversized these objects, you can do these nice pushing behaviors with your whole body motions and different contact locations, and just to help to generate the power to the bot, right? So we think it is kind of similar story for the humanoid itself, right? We can somewhat mimic that or use a optimization framework to find out these optimal poses for different kind of like object and shapes, right? So we propose a kinodynamic pose optimization to kind of figure out at the current instances of the kinematics and dynamic relationships, how to represent a pushing pose or how to generate an optimal pushing pose that is suitable for certain objects or certain scenarios, right? So with that framework, we can then formulate a reduced order model or a single rigid body dynamics model for both the robot and the object and stitch them together with these contact forces in between. So you can represent the interaction of robot and the environment, and robot with the object, object with the environment. So it's like environment, robot, object, sort of a reduced order model. Okay. So with these modeling strategies explained, we're putting them back into our hierarchical framework, right? So for the high level, we'll still have a multi-contact planning or some sort of a pose optimization framework to figure out, these guided pose or figure out some of these trajectory evolutions or contact behaviors or contact transitions, right? And on the mid-level, we can switch between, different local manipulation modes or different local manipulation models for different kind of tasks within a unified framework, right? So with this unified framework, in simulation we can generate these nice motions of throwing 2-kilogram ball while the robot is only around like 16 kilograms, so it's pretty heavy for the robot, and doing these nice stepping behaviors while throwing, right? That's all thanks to these predictions of contact schedules within the MPC window. Okay. And also we can do this nice perturbation resistant pushing behaviors with a very heavy object that is heavy as the robot, right? So when it pushes, the robot will be able to adapt to it. Okay. And we also compare some realistic scenarios where we put the robot into action within these industrial settings. So we'll ask the robot to pick up the box and then drop it on the conveyor belt, turning 90 degrees. Right, so with the baseline method, which are mostly just a whole body control base without any future contact information, that you have to do each of these tasks sequentially, right? And with our proposed method here, the hierarchical control with full contact timing schedule, we can overlap these nice actions together, right? So turning and picking up together and turning and dropping off together. So that results in a nice reduction in this task times, right? Okay, and here are some more videos of the robot just walking around with heavy payloads. Maybe one of the days they will be able to carry your groceries for you and hold you responsible about that. Okay, so with that, we'll get into the next part or the last part of the talk, which will be adaptive frequency locomotion and manipulation via learning augmented MPC. And thank you for everyone for staying until here. This part will try to represent a complex gate frequency behavior decision-making behavior through a data-driven approach, and then combine the traditional numerical optimization solving mechanism with learning augmented components. Okay, so that leads to a sort of a natural discussion or ongoing discussion of model-based versus learning-based control within the realm of motion control and motion planning, right? So I would like to refer to a very nice analogy from Professor Sanbei Kim's talk, right? He compares the model-based approach as a gentle and obedient butler that is able to obey every constraints, every dynamics that you put it, and do this very nice task hierarchies in strict mathematical fashion, right? And on the other hand, you have this learning base that is a wild and tamed beast. It is very powerful, or the other way around. It is not controllable, but it's very powerful. So it will be able to do these nice end-to-end training with diverse domain randomizations and to discover these motor level skills very effectively within a short time frame. So the idea is how we combine these two or how we merge these two together to use the nice behaviors or representative behaviors of the model-based approach to contain or to tame the beast so you can fully leverage the learning-based power, right? So this will be our try to, somewhat tame the beast here with our butler. So the current learning augmented MPC method that we see nowadays, right? So for example, this work here is predicting nonlinear complex rigid body inertia in the future horizons of MPC, so it can retain a linear relationship and able to do these adaptive variable frequency behaviors, variable inertia behaviors within the MPC dynamics, right? And then our lab also does RL augmented MPC that is using, learning a residual dynamics for the MPC simplified rigid body dynamics for a more robust and adaptive behavior here. So if you see, they're mostly, the learn policy is somewhat independent of the MPC and is more of a feed-forward fashion that is, within this optimization or within this hierarchy, right? So if you remove that learn policy, MPC will still work. The policy is only sort of modifying or implementing or complementing some of these mathematical models within MPC. What we want to propose is more of a more deep integration, right? So we call it the gate-net augmented MPC, where we infuse the learning based policy in numerical optimization for solving in terms of the solving mechanism. So we seek a deeper connection between the two. On the framework level, we still see this nice hierarchical fashion, right? So we have the high level, mid level, and low level, right? And inside of the mid level, though, we'll have a sort of an iterative hierarchy, what we call. So inside of the sequential QP, and the learn policy would iterative until convergence. And with this mid-level MPC, we want to determine the step location, step duration, and contact forces all at once with just one reduced order model framework. Okay, so here are some inspirations we draw from the past works. This is from MIT using a whole body dynamics-based MPC that is very nice within these push recovery behaviors. But if you look at the stepping here, it is still fixed frequency, and we think just adding another variable of adaptive frequency might not be interesting enough to address this problem. And plus, we want to use these adaptive frequency and also these reduced order modeling strategies to address this problem. So that leads to our kind of overview of our idea here, right? So for the whole body dynamics, a very nice representation of the whole body model. But for the centroidal dynamic itself, it is, although a good representation of the whole body inertia evolution of all the limbs and everything, it does not have any proper relationship or dynamics representation of step duration and step location. So that is addressed really well inside of the whole body dynamic. So that's why you see a lot of these nice contact implicit works, they're using whole body dynamics model to do this contact implicit planning. So what we want to do is, instead of just using the whole body dynamics within the MPC with very strong computation power, right? We want to borrow some of that nice dynamic couplings there with step duration, step locations, put it into our centroidal dynamics, and somehow implement it so that we can use a reduced order model, still retain that fidelity of the dynamics of the steps. Okay, so we propose a whole body MPC with step frequency optimization. Instead of solving it online, we're solving this within, or we're running this inside of an optimization, inside of a simulation to collect a bunch of different data, scales of data to kind of relate the state variables to the step duration at any given point, and put it into what we call a gate network. And we use this gate network to output a DTMPC that is representative to the next step duration for at certain state, right? And then that part will be implemented into the centroidal dynamics here to represent the step duration decision making, and that only leaves this step location as well as the contact force for us to solve, which is just a bilinear constraint we can throw into a SQP solver, which will integrate our GateNet in. Okay, so this is what it looks like in the sequential QP solving mechanism with our GateNet. So a strict hierarchical or like an iterative hierarchy here. So on the top level, we linearize the convex MPC subproblem to a QP and solve it very efficiently. With that local solution, we put it into GateNet and infer it to get the DTMPC prediction for the next iteration and for updating the centroidal and momentum, centroidal pulse and momentum reference trajectory. So it's more in line with our kinematic representation within this pulse. So we'll iterate this process until the convergence of the solution. And then you'll be able to do the step duration, step location, and step forces or contact forces all at once. Okay. So comparing to some of the state-of-the-art solving approaches, for example, the traditional sequential QP solvers with whole body dynamics and explicit kinodynamics model, they're very costly solving to a absolute convergence or to a very accurate representation. And there's more iterations there. Comparing to a alternating direction method where, in this case, it has 3 variables solved, so 3 directions, and that exhibit a longer average or larger number of iterations here, also not really ideal in terms of the solve time online. Our proposed method not only will be able to cut down the computation speed by computation cost by a lot, but also we retain some of these nice kinematic couplings of kinematic couplings of the step duration and step location, as well as ensuring the kinematic visibility along the trajectory. Okay. So this is within the simulation, we're doing some stepping stone locomotion, right? So there's hard constraints on the foot locations and be able to traverse this terrain. And so that leads to how do we transfer this to hardware? Because naturally, there's always some sorts of gaps between hardware and simulations when it comes to learning, right? So what we want to achieve here with this comparison is we want to validate that our GateNet model trained on noise-free simulation data will be able to compare to or be able to deploy in a real world scenario with different kind of IMU and sensor encoder noises, right? So this is a list of parameters we chose for the noise, and in the worst case scenario, our methods trained with noise-free case is only 0.39 millisecond performance difference from the hardware realistic noises models, right? So that is pretty much zero-shot hardware transfer we can do. So we did it with all that. And this is the behavior of the adaptive system with some of the companies with all the as well as the information over this these virtual terrain maps and explicit constraint here, it won't step within the gap here. Another video of walking over both the obstacles and the gaps together. Okay. And then with that, we can also do some more difficult manipulation, local manipulation tasks. Like, for example, pushing this card with a stack of robots, not knowing the dynamics of the robot, that will be same frequency to deploy this. All right. So with that, I think that's pretty much it for the works that we have done so far. So there is a summary of contributions, right? So we propose a highly dynamic and reactive humanoid local manipulation model predicted control with single rigid body dynamics. And then building on top of it, we're proposing the adaptive frequency of hierarchical optimization with reduced order modeling strategies for humanoid robots to be very agile and dynamics in these locomotion behaviors. And parallelly, we're also investigating a hierarchical whole body local manipulation framework for a very efficient and unified local manipulation control that's using whole body motion as well as these contact timing informations. And lastly, we use a learning-infused optimization solving mechanism for a robust and adaptive locomotion and manipulation learned from the lessons that we had from the previous research. And all of that method or all of that proposed approaches we validated through extensive experimental validations through our in-house bipedal locomotion, bipedal humanoid hardware platforms. Okay. So with that, I would like to thank the dissertation committee for being here today and guiding our research to this point. Specifically, I want to thank Professor Quan Nguyen for being the nicest PhD advisor and some of these collaborators within our lab here who are here today, as well as my MS collaborators and some mentees here, as well as these outside collaborators we have been working with along the way. Okay, so with that, my deepest gratitude to my family and friends as well. Making it a little bit easier for me or less painful in the journey. And with that, I would like to thank everyone. And then, yeah, that's it for the presentation.
Thank you. Next, we will open the floor for some questions from the audience.
Yes.
Have any question?
Great question.
Yes.
Great design choices and heuristics and ready to model. So the numbers are really nice. But thanks to this company named NVIDIA, we have edge GPUs. So where do you think MPC can be benefited from this computational advance, like GPU-based compute that are available for on-board devices?
Yeah, like I think we have had this sort of discussion previously because of these nice sort of parallel computing components available on the market. You can deploy actually these nice MPCs into training environments, so you can do more of this combined RL and MPC method. So I think the future is still somewhat in between or somewhat combined. You cannot really ditch anyone, and this will be a nice try to or a nice entry to explore that combined method. Right. Yes.
Yes, thank you for your great talk. I have several questions.
Okay.
The first two questions are about the payload part.
Yes.
So the first question I'm thinking of is that you said your method can enhance the amount of the payload you can hold.
Yeah.
I'm curious about whether the robot has a measurement of the upper limit of it. For example, if you give it something too heavy, then it knows once it touches it, it can throw it away.
Okay. Yeah, that's a great question. See for let me answer the first part of it first, right? Like how much can we really handle on the robot? So we really trying to push the limit for the robot, how much payload it can handle, right? So for this standing case, it will be able to handle around like 50% of its body weight. So this 16-kilogram robot is capable of handling 8 kilograms of a load. And also for the stepping would be sort of like half of it. But for the second part, if we're talking about throwing and keeping balance while having too much of a payload, right? we actually had a little bit of investigation on that. Like, can we really use some of these nice behaviors of manipulation to remain balanced? Like, say, for example, if you're carrying a payload and then someone pushes you and you kind of like use the payload to generate some sort of a counter moment to react to this disturbance. So it is possible, but the challenge is how to do it very effectively or efficiently. So our method of the hierarchical optimization in the second section, right? So uh, this one here is sort of like kind of like a preliminary work for that idea they were trying to explore, right? So if you're doing this push recovery and you're holding some object, and you can throw that object to generate an even a better or larger counter moment to remain balanced, right? So I think it's possible, and it's just requires a bit of more modeling strategies to achieve that, like contact timings as well. Yeah.
Yeah, and another question is when you are showing the video of the robot holding the two payloads at both of its hand, you mentioned it can do grocery. And the question I'm thinking is when we are doing the grocery, the thing is also always oscillating.
Yes.
And I'm curious about whether your robot can handle this effect. If there is a pendulum.
That is a great question. So within some areas of these exact location of the COM of this object, it is still possible to handle, within certain, limit. But I think to be more sort of stable, you will need some sort of estimation of the payload or center mass, like for example, using some vision stacks to figure out where that is. Yeah.
Thank you. And my last question is about the GateNet you mentioned at last. I'm curious about what's the exact input and output of the neural net.
Okay, yeah, for sure. Let me see. Let's go back to this slide here. Okay, so you see our GateNet here, the input space or feature space include all of the joint and the COM state of the robot. Right, so pretty much all the information you can get from the sensors, from the IMUs. At the same time, also like the step duration or step location for the robot. So we use all of that information and then relate it to a DT of MPC, which is one of the optimization variable within the whole body dynamics MPC here.
So much.
Yes. Thank you. Yes, Nathan.
Thank you for the thorough talk. I feel like every time I hear you talk, I learn something new. So I just have a question about the variable or adaptive gate frequency study. What forms of perception and sensor feedback did you use, particularly for the one where you're pushing an object?
Yeah, so for the pushing of object, I should have mentioned it is entirely blind, and even walking is entirely blind. So we're so let's go back to here. Maybe this will be a good slide here. Yeah. So the robot does not really know the objects here, is treating it as entirely as a disturbance. Say, for example, it's similar to you're like constantly pushing a robot because of this disturbance, right? For local manipulation. So this will, the robot sees this as a disturbance and does not really see it as a object here. But for some of these, stepping stones behaviors, they are more like we're defining or predefining these terrain gaps for the robots so that it knows ahead of time where these gaps are.
Do you think it would improve the performance of your gate planner if you add some sort of
vision feedback? Yes. So yeah, that's actually in our future work. We mentioned that it would be really nice if we can really do this autonomously with proper and very robust vision feedback, because I think one of the challenges is if we're planning these steps and there's any like sort of inconsistencies with the planned location as well as the actual location, there might be, it could fail. Yeah. So yeah. So simply put, that's kind of like a preview of the terrain with the predefined data is more of the first step, and also is one step preview of the data is similar to what you do with a onboard vision stack, right? So you can scan your next step online as well, right?
Okay, thank you. For the next part, we'll have a closed session between comments. But I will ask the audience to the outlets, but don't run away. In case it's fast, we will go to
Thank you, guys.
you.
Okay, and thank you for online attendees. I will now close this Zoom section. Thank you for attending.
Yes.